Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Legendre Differential Equation and Polynomials from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. First, importance of Legendre equation in physics is explained and its derivation from Laplace equation is sketched. Secondly, series solutions of the Legendre equation are obtained for the case of integer values of the parameter n. It is explained as to how one solution becomes a polynomial of order n called the Legendre polynomials. Detailed study of the properties of the Legendre polynomials is undertaken. Brodrick's formula is derived. Properties of zeros of Legendre polynomials are studied. The generating function is derived and the recurrence relation is obtained. Integrals involving products of Legendre polynomials are obtained, from which follow the orthonormality property of these polynomials. Finally, the complete solution of the Legendre equation is discussed briefly. Let me now introduce you to Legendre differential equation. Legendre differential equations are one of the most important equations. They arise as a result of solving Laplace equation written in spherical polar coordinates. The equation is given by 1 by r square del by del r of r square del by del r plus 1 by r square sine theta multiplied by del theta of sine theta del theta plus 1 by r square sine square theta multiplied by del phi square. All terms are enclosed in a square bracket which is multiplied by capital V and is equated to 0. V is given as r raised to power n into yn, a function of theta and phi. We seek a solution of this equation in the form capital V is equal to r raised to power n into yn of theta phi, where n is an integer. Then the equation is 1 by sine theta multiplied by del theta within the brackets sine theta del yn by del theta brackets close plus 1 by sine square theta into del 2 yn by del phi square plus n into n plus 1 into yn is equal to 0. The function yn theta phi is usually called spherical harmonic of degree n. If we further seek a solution of the spherical harmonic in a separable form given by yn of theta phi is equal to e to the power plus minus im phi into w of z, where z is equal to cos theta. We get the equation 1 minus z square into d2w by dz square minus 2z into dw by dz plus within the brackets n into n plus 1 minus m square by 1 minus z square bracket close into w is equal to 0. This is the associated Legendre equation. In the case of greater interest, m can take only integer values 0, 1, 2 and so on till n. Finally, if we consider the special case of m is equal to 0, we obtain the Legendre equation given by 1 minus c square into d2w by dz square minus 2z dw by dz plus n into n plus 1 into w is equal to 0, or equivalently d by dz into within the brackets 1 minus c square into dw by dz bracket close plus n into n plus 1 into w is equal to 0. Next we move on to study the solution of the equation given by Legendre polynomials. Although the parameter n can take any value, even complex values, the case of general interest is one in which n is a non-negative integer, and that is the case we will study. We can easily verify that singularity at z is equal to plus minus 1 is regular with the exponent taking value 1, and the 1 at infinity is also regular with the exponent taking values minus n and n plus 1. The origin is an ordinary point of the equation and is given by z is equal to 0. If we rewrite the equation in the form d2w by dz square minus 2z divided by 1 minus z square multiplied by dw by dz plus n into n plus 1 into w by 1 minus z square equals 0. We see that pz is equal to minus of 2z divided by 1 minus c square. This is equal to summation over I going from 0 to infinity pi z raised to power I, which is also equal to minus 2z within the brackets 1 plus z square plus z raised to power 4 plus so on. Similarly, q of z is equal to n into n plus 1 divided by 1 minus c square. This is equal to summation over I going from 0 to infinity over the terms qi z raised to power I. This equals n into n plus 1 and within the brackets 1 plus z square plus z4 plus so on. Now, the radius of convergence of both the series is capital R is equal to 1. We seek a solution of the form w of z is equal to c0 plus c1z plus c2 z square plus so on. This may be represented by the series sum summation over I going from 0 to infinity ci z raised to power I. The radius of convergence of this series will be at least equal to 1. Putting into the Legendre equation, we obtain 1 minus z square into within the brackets 2c2 plus 2 into 3 c3z plus so on brackets close minus 2z within the brackets c1 plus 2c2z plus so on bracket close plus n into n plus 1 into within the brackets c0 plus c1z plus c2z square plus so on bracket close is equal to 0. On equating the coefficients of various parts of z, we obtain the following relations: 2 times c2 plus n into n plus 1 c0 is equal to 0. Next, 2 into 3c3 minus 2c1 plus n into n plus 1 c1 is equal to 0. Next, 3 into 4c4 minus 2 into 3c2 plus n into n plus 1 C2 is equal to 0. In general, the relation is I plus 1 into I plus 2 into Ci plus 2 minus I into I plus 1 into Ci plus n into n plus 1 into Ci is equal to 0, where I takes the values 0, 1, 2 and so on. The coefficients C0 and C1 are arbitrary and the above equations can be solved for the rest of the coefficients in terms of these two. Since the indices occurring in the recurrence relation above differ by 2, so we obtain two separate sets of relations, one involving even indices only and the other odd indices only. Thus, C2 is equal to minus of n into n plus 1 C0 divided by 2. C4 is equal to 2 into 3 minus n into n plus 1 C2 divided by 3 into 4. This is also equal to minus of n minus 2 into n plus 3 into C2 divided by 3 into 4, or may be simplified to obtain n into n plus 1 into n minus 2 into n plus 3 C0 by 4 factorial. C3 is equal to 2 minus n into n plus 1 divided by 2 into 3. The entire thing is multiplied by C1 and may be simplified to obtain the relation C3 is equal to minus of n minus 1 into n plus 2 into C1 by 3 factorial. Similarly, C5 is equal to 3 into 4 minus n into n plus 1 divided by 4 into 5. The entire thing is multiplied by C3, which results after simplification to give C5 is equal to minus of n minus 3 into n plus 4 into C1 by 4 into 5. Or I can rewrite the expression as n minus 1 into n plus 2 into n minus 3 into n plus 4 C1 divided by 5 factorial. Continuing in this way, we obtain the general expression for the even and odd indices respectively, given by C2i is equal to minus 1 raised to power I into n plus 1 into n minus 2 into n plus 3 so on till n plus 2i minus 1 into C0 divided by 2i factorial. C 2i plus 1 will be equal to minus 1 raised to power I into n minus 1 into n plus 2 into n minus 3 into n plus 4 and so on till n plus 2i multiplied by C1 divided by 2i plus 1 factorial. The general solution of the Legendre equation can therefore be written as W of z is equal to C0 plus C1z plus C2z square plus C3z cube plus so on. This is equal to C0 times Sn of z plus C1 times Tn of z, where Sn of z is equal to summation over I going from 0 to infinity minus 1 raised to power I into n plus 1 into n minus 2 into n plus 3 so on till n plus 2i minus 1 multiplied by z raised to power 2i divided by 2i factorial. Tnz is equal to summation over I going from 0 to infinity minus 1 raised to power I n minus 1 into n plus 2 into n minus 3 into n plus 4 and so on till n plus 2i multiplied by z raised to power 2i plus 1 divided by 2i plus 1 factorial. These two solutions, Sn of z and Tn of z, are linearly independent. One consists of only even powers of z and the other of odd powers. Hence, we have obtained the general solution of the Legendre equation. In general, the radius of convergence of the series solution is given by capital R is equal to 1. The series solution is valid for all values of n, including even complex values. For integer values of n, one of the two series terminates. If n is even, the series for Sn of z terminates and reduces to a polynomial of degree n. The other solution is an infinite power series. If n is odd, the series for Tn of z terminates and reduces to a polynomial of degree n. The other solution is an infinite power series. These polynomial solutions with proper normalization are the Legendre polynomials. If n is not an integer, both the solutions are power series with unit radius of convergence. These are called Legendre functions. Now we discuss an alternative method. Here, we could have started with the point at infinity, which is a regular singular point with exponents minus n and n plus 1. In that case, we attempt a series solution of the form w is equal to z raised to power minus alpha into within the brackets c naught plus c1 z raised to power minus 1 plus c2 into z raised to power minus 2 plus so on brackets close. The solution with the exponent minus n and n plus 1 are respectively given by w of z is equal to a times z raised to power n into within the brackets 1 minus n into n minus 1 by 2 into 2n minus 1 multiplied by z raised to power minus 2 plus n into n minus 1 into n minus 2 into n minus 3 multiplied by z raised to power minus 4 divided by 2 into 4 into 2n minus 1 into 2n minus 3 minus and so on brackets close plus b into z raised to power minus n minus 1 multiplied by within the brackets 1 plus n plus 1 into n plus 2 into z raised to power minus 2 divided by 2 into 2n plus 3 plus n plus 1 into n plus 2 into n plus 3 into n plus 4 into z raised to power minus 4 divided by 2 into 4 into 2n plus 3 into 2n plus 5 minus and continues so on. So, Wz is equal to a times W1 of z plus b times W2 of z and W of z is given by c multiplied by W2 of z. Thus, we have again found two linearly independent solutions of the Legendre equation. The first solution is a polynomial solution and is valid for all z, while the second is an infinite power series convergent for mod of z greater than 1. Next, we move on to discuss about the Legendre polynomials. In solution 1, let us take the constant a to be a equal to 2n factorial divided by the square of the quantity 2 raised to power n into n factorial. With this value of the constant, the polynomial solutions are the Legendre polynomials of degree n, where w is equal to Pn of z. Pn of z is equal to summation over I going from 0 to r minus 1 raised to power I into 2n minus 2i factorial into z raised to power n minus 2i divided by 2 raised to power n I factorial into n minus I factorial into n minus 2i factorial. Here r is equal to n by 2 if n is even and r is equal to n minus 1 by 2 if n is odd. The first few Legendre polynomials are therefore given by P0 of z is equal to 1, P1 of z is equal to z, P2 of z is equal to 1 by 2 multiplied by 3z square minus 1. P3 of z is equal to 1 by 2 multiplied by 5z cube minus 3z. When we discuss Legendre polynomials, it is very important to discuss Rodrich's formula. So, let us evaluate the derivative which is given by nth order derivative of z raised to power 2n minus 2i with respect to z. So, d by dz raised to power n into z 2n minus 2i is equal to 2n minus 2i multiplied by 2n minus 2i minus 1 and so on till n minus 2i plus 1 into z n minus 2i. This is equal to 2n minus 2i factorial into z raised to power n minus 2i divided by n minus 2i factorial. On substituting this into the expression for P and z, we get Pn of z is equal to summation over I going from 0 to r minus 1 raised to power I divided by 2 raised to power n I factorial into n minus 2i factorial multiplied by nth order derivative of z raised to power 2n minus 2i with respect to z. The equation can be simplified to obtain Pn of z to be equal to 1 by 2 raised to power n into n factorial multiplied by the nth order derivative with respect to z of summation over I going from 0 to r minus 1 raised to power I n factorial into z raised to power 2n minus 2i divided by I factorial into n minus 2i factorial. For I is equal to r plus 1, 2n minus 2i will be equal to 2n minus 2r minus 2 is equal to n minus 2 for n even and n minus 1 for n odd. Therefore, in either case, the nth derivatives of terms beyond I is equal to r is 0. Hence, we can extend the summation beyond r up to n and rewrite the above equation as Pn of z is equal to 1 by 2 raised to power n into n factorial, then multiplied by the nth order derivative with respect to z of summation over I going from 0 to n minus 1 raised to power I into n factorial into z raised to power 2n minus 2i divided by I factorial into n minus 2i factorial. Now, from binomial theorem, we know that summation over I going from 0 to n of minus 1 raised to power I n factorial into z raised to power 2n minus 2i divided by I factorial into n minus 2i factorial is equal to z square minus 1 raised to power n. Thus, we finally obtain Pn of z is equal to 1 by 2 raised to power n into n factorial multiplied by the nth order derivative of z square minus 1 raised to power n with respect to z. This is the Rodrigues formula for the Legendre polynomials. Let us now consider zeros of Legendre polynomials given by the equation z square minus 1 raised to power n, which equals to z minus 1 raised to power n into z plus 1 raised to power n. The equation has only two roots given by minus 1 and 1, each of multiplicity small n. Now, by Gauss-Lucas theorem, all roots of derivatives of z square minus 1 raised to power n lie in the interval minus 1 to 1. On applying the theorem n times, it follows that all roots of Pn of z lie in the interval minus 1 to 1. Now, we verify by direct expansion of z square minus 1 raised to power n derivative taken n times with respect to z that Pn of plus minus 1 is not equal to 0. Hence, all the zeros of Legendre polynomials are real and lie in the open interval minus 1 to 1. If the Legendre polynomial had a double root at z is equal to a, it will be a solution of the equation given by 1 minus z square into d2w by dz square minus 2z into dw by dz plus n into n plus 1 into w is 0, where the initial conditions are specified as w of a is equal to 0 and w prime of a is equal to 0. But the solution of the initial value problem is unique and is z is equal to 0. Hence, all the n roots of the Legendre polynomial of order n are real, distinct and lie in the open interval between minus 1 to 1. Next, we discuss about the generating function for Legendre polynomials, which leads to Laplace first integral. If we use Cauchy's formula for the nth derivative of an analytic function for the Rodrigues formula, we obtain Pn of z is equal to 1 by 2 pi I, the contour integral of t square minus 1 raised to power n by 2 raised to power n into t minus z raised to power n plus 1 dt, where C is any closed contour surrounding the point t is equal to z. This is called Schläfli integral formula. For the contour C, let us take the circle modulus of t minus z is equal to square root of modulus z square minus 1. Then, on the contour C, t will be equal to z plus under root of z square minus 1 multiplied by e raised to power I into phi, where phi varies from minus pi to pi. Making this change of variable, we have t square minus 1 is equal to 2 times square root of z square minus 1 into e raised to power iota phi multiplied by within the brackets z plus square root of z square minus 1 cos phi brackets close. This is equal to twice of t minus z multiplied by within the brackets z plus square root of z square minus 1 into cos phi. Hence, From Lafleur integral formula, we obtain Pn of z is equal to 1 by 2 pi definite integral over phi within the limits minus pi to pi for the term z plus under root of z square minus 1 cos phi within the brackets raised to power n. Further, the integrand is an even function of phi. Hence, Pn of z is equal to 1 by pi definite integral over phi going from limits 0 to pi for the term within the brackets z plus under root of z square minus 1 cos phi brackets close raised to power n. This is known as the Laplace first integral for Legendre polynomials. We can use this integral form for the Legendre polynomials to find a generating function for them. Let us sum the series summation over n going from 0 to infinity t raised to power n Pn of z using Laplace first integral. So, summation over n going from 0 to infinity t raised to power n Pn of z is equal to summation over n going from 0 to infinity, then within the brackets t raised to power n multiplied by 1 by pi, then the integral over phi going from 0 to pi, within the brackets the term is given by z plus square root of z square minus 1 cos phi brackets close raised to power n. It can be shown that the integration and infinite sum can be interchanged so that summation over n going from 0 to infinity t raised to power n Pnz is equal to 1 by pi definite integral over phi going from limits 0 to pi 1 divided by 1 minus tz minus t times square root of z square minus 1 into cos phi. This is an elementary integral. On evaluating it, we get summation over n going from 0 to infinity t raised to power n Pn of z is equal to 1 by square root of 1 minus 2tz plus t square. Hence, we have the generating function given by capital G of tz is equal to 1 by square root of 1 minus 2tz plus t square. It can be written in the series form as summation over n going from 0 to infinity t raised to power n Pn of z. If we put z is equal to 1 and minus 1 in the generating function, we get 1 minus 2t plus t square raised to power minus 1 by 2 is equal to 1 divided by 1 minus t, which in turn can be written as 1 plus t square plus so on. It can be written as series sum summation over n going from 0 to infinity t raised to power n Pn of 1. Hence, Pn of 1 is equal to 1, where n goes from 0, 1, 2 and so on. Similarly, if we put z is equal to minus 1, we get 1 plus 2t plus t square raised to power minus 1 by 2 is equal to 1 by 1 plus t, which gives 1 minus t plus t square minus and so on. This is equal to the series summation over n going from 0 to infinity t raised to power n Pn of minus 1. Hence, Pn of minus 1 is equal to minus 1 raised to power n, where n takes the value 0, 1, 2 and so on. Next, we discuss the recurrence relations. Using the generating function, we can deduce certain recurrence relations between Legendre polynomials and their derivatives of different orders. We can easily verify that the generating function satisfies the differential equation given by 1 minus 2tz plus t square within the brackets multiplied by del of capital G by del t is equal to the product of z minus t into capital G of tz, where the capital G is the generating function. Now, using the expression for generating function, we obtain the equation as 1 minus 2tz plus t square within the brackets multiplied by summation over n going from 0 to infinity n into t raised to power n minus 1 into Pn of z. This can be simplified to get z minus t multiplied by summation over n going from 0 to infinity t raised to power n into Pn of z. On equating the coefficients of t raised to power n minus 1, we have the recurrence relation n multiplied by Pn of z minus 2n minus 1 into z into Pn minus 1 of z plus n minus 1 into Pn minus 2 of z is equal to 0. Let us number this equation as 1. Similarly, on using the relation t multiplied by del of capital G by del t is equal to z minus t multiplied by del of capital G by del z. Thus, we get the second recurrence relation as z multiplied by d by dz of Pnz minus d by dz of Pn minus 1z. This is equal to n Pn of z. Let us say the equation as number 2. If we now differentiate equation 1 with respect to z, then use 2 with n tending to n minus 1, we obtain the third recurrence relation given as within the brackets dPn of z by dz minus z times dPn minus 1 of z divided by dz brackets close is equal to n into Pn minus 1 of z. Let us say it as equation 3. We can use these three recurrence relations to derive a few more such relations. For example, if we multiply equation 2 by z and subtract equation 3 from it, we get z square minus 1 into d of Pnz by dz is equal to n into z into Pn of z minus n into Pn minus 1 of z. Let us say it as equation number 4. Now we discuss the integrals involving products of Legendre polynomials. Legendre polynomials Pm of z and Pn of z satisfy respectively the differential equations given as d by dz of 1 minus z square Pm prime plus m into m plus 1 into Pm is equal to 0. The other equation is d by dz of 1 minus z square Pn prime plus n into n plus 1 Pn is equal to 0. Here, a dash refers to differentiation of p with respect to z. Now, we multiply the first of these equations by Pn and second by Pm and subtract the two. So, we get m into m plus 1 minus n into n plus 1 within the brackets multiplied by Pm into Pn is equal to Pm times d by dz of within the brackets 1 minus z square Pn prime brackets close minus Pn into d by dz of within the brackets 1 minus z square Pm prime, or I can write it as m minus n into m plus n plus 1 Pm into Pn is equal to d by dz of within the brackets 1 minus z square into Pm Pn prime minus Pn Pm prime brackets close. On integrating the equation between z1 and z2, we have m minus n into m plus n plus 1 multiplied by a definite integral over z going from the limits z1 to z2, Pn is equal to within the brackets 1 minus z square into Pn prime minus Pn prime brackets close over the limits z1 to z2. Now, by using recurrence relation on the right hand side, we get 1 minus z square into Pn prime minus Pn prime is equal to Pm multiplied by within the brackets n into Pn minus 1 of z minus n into z into Pn of z brackets close minus Pn multiplied by within the brackets m into Pm minus 1 of z minus m into z into Pm of z brackets close. This is equal to n into Pm Pn minus 1 minus m into Pm minus 1 plus m minus n into z into Pn. Hence, when m is not equal to n, integral over z going over the definite limits z1 to z2 of the term Pn is equal to 1 by m minus n into m plus n plus 1. The entire thing is multiplied by within the brackets n into Pm minus 1 minus m into Pm minus 1 plus m minus n into z into Pn with the limits substituting from z1 and z2. This is the required result for m not equal to n. When m is equal to n, we make use of recurrence relations 1 and 2, from which we get 2n plus 1 into Pn square minus 2n minus 1 into Pn minus 1 square is equal to 2 times Pn into within the brackets z Pn prime minus Pn minus 1 prime brackets close minus twice of Pn minus 1 within the brackets Pn prime minus z times Pn minus 1 primes bracket close plus Pn square plus Pn minus 1 square. This is equal to d by dz of within the brackets z into Pn square plus z into Pn minus 1 square minus twice of Pn minus 1 into Pn bracket close. We now integrate to obtain the integral over z over the definite limits z1 to z2 for the term 2n plus 1 Pn square minus another integral over z going from the limit z1 to z2 for the term 2n minus 1 into Pn minus 1 square is equal to, within the brackets I write z Pn square plus z Pn minus 1 square minus 2 Pn minus 1 Pn with the limit substituting z1 and z2. We next put n is equal to 1, 2, 3 till m successively in this equation and add. So, we obtain 2n plus 1 into the definite integral over z going from z1 to z2 for the term pm square minus the integral over z going from z1 to z2 for the term p naught square is equal to, within the brackets, z times p naught square plus twice of z within the brackets p1 square plus p2 square plus pm minus 1 square bracket close plus z pm square minus 2 again multiplied by, within the brackets, p0 p1 plus p1 p2 plus so on pm minus 1 pm bracket close. The main bracket is also closed and the limits goes from z1 to z2. Since p naught of z is equal to 1, this implies the integral over z for p naught square is equal to z and p1 of z is equal to z. The above equation becomes 2m plus 1 multiplied by the definite integral over z going from the limits z1 to z2 pm square is equal to, within the main brackets I write 2z multiplied by, within the small brackets, p1 square plus p2 square plus pm minus 1 square bracket close plus z times pm square minus 2 multiplied by, within the brackets, p1 p2 plus so on till pm minus 1 pm. The bracket is closed and the main bracket is also closed and the limits are substituted as z1 and z2. Thus, this is the result for the integral of the square of Legendre polynomials. Next, we proceed towards the orthonormality of Legendre polynomials. The results 5 and 6 that we have derived are general. They apply to any limits z1, z2. In particular, let the limits be minus 1 and 1. Since Pn of 1 is equal to 1 and Pn of minus 1 is equal to minus 1 raised to power n, so the quantity on the right hand side of equation 5 is 0. So we get the definite integral over z going from minus 1 to 1 Pn is equal to 0 for m not equal to n. Similarly, from equation 6 we get the definite integral over z going from the limits minus 1 to 1 for the term pm square is equal to 2 by 2m plus 1. The two relations can be written together by introducing the Kronecker delta function, represented as the definite integral over z going from the limits minus 1 to 1 over the term pn is equal to 2 by 2m plus 1 into delta mn. Legendre polynomials form an orthonormal set over the interval z lying between minus 1 to 1. This was the reason for choosing the specific value for a. Legendre equation arises in the solution of Laplace equation. The independent variable z actually stands for cos of theta. As theta varies from 0 to 2 pi, cos of theta varies from minus 1 to 1. So, minus 1 to 1 is the natural range for the variable in Legendre polynomials. Our next aim is to find the complete solution. The Legendre equation has regular singularities at z is equal to plus minus 1 where the exponent is 1. Hence, the exponent difference is 0 at both the singularities. So, one of the solutions has a logarithmic singularity. To find the solution, we use the usual method of obtaining the second solution when one solution is known. For this purpose, we make the substitution w of z is equal to Pn of z into v of z. Substitute this in Legendre equation and we find that v of z satisfies the equation 1 minus z square into Pn of z into the double derivative of v of z plus twice of within the brackets multiplied by within the brackets 1 minus z square into Pn prime of z minus z into Pn of z brackets close multiplied by v prime is equal to 0. On multiplying by Pn of z, this equation can be written as within the brackets I write z square minus 1 into Pn square of z into v prime of z brackets close, then the prime of the entire thing in the brackets is equal to 0. We integrate this equation twice and we get v is equal to a plus b times the integral of dz divided by z square minus 1 into Pn square of z. Hence, the complete solution of the Legendre equation is w is equal to a times Pn of z plus b times Pn of z multiplied by the integral over dz divided by z square minus 1 Pn square of z. To this end, we know that Pn of z has n distinct zeros between minus 1 and plus 1. Therefore, Pn square of z has n distinct double zeros between minus 1 and plus 1. From the theory of partial fractions, we can write the integrand as 1 by z square minus 1 into Pn square of z is equal to 1 divided by 2 into z minus 1 minus 1 by 2 into z plus 1 plus summation over I going from 1 to n of the terms ai by z minus zi plus bi by z minus zi square. Let us now write Pn of z is equal to z minus zi into f of z. If we substitute this in the Legendre differential equation, we find that f of z satisfies the equation 1 by 2 multiplied by z minus zi multiplied by within the brackets 1 minus z square into f double prime of z minus 2z into f prime of z plus n into n plus 1 into f brackets close plus within the brackets again 1 minus z square into f prime of z minus z times f brackets close is equal to 0. On putting z is equal to zi, the first term vanishes and we have 1 minus zi square into f prime of zi minus zi into f of zi is equal to 0. Now, the coefficients ai are the residue of 1 by z square minus 1 into Pn square of z at z is equal to zi. ai is equal to 1 minus z square into f prime zi minus zi into f zi within the brackets multiplied by minus 2 divided by 1 minus zi square into the cube of f of zi. This is equal to 0. Hence, 1 by z square minus 1 into Pn square of z is equal to 1 by 2 into z minus 1 minus 1 by 2 into z plus 1 plus summation over I going from 1 to n of the terms bi by z minus ci square. Now, on performing the integral, we obtain w is equal to a times Pn of z minus b times within the brackets half multiplied by Pn of z into the natural log of z plus 1 divided by z minus 1 plus Pn of z multiplied by the summation over I going from 1 to n of Bi by z minus Zi. This gives W to be equal to A times Pn of z minus B times, within the brackets I have half multiplied by Pn of z into natural log of z plus 1 by z minus 1 minus Wn minus 1 of z, brackets close. Here A and B are arbitrary constants and Wn minus 1 of z is a polynomial of degree n minus 1. We next take the second solution of the Legendre equation to be Qn of z is equal to 1 by 2 into Pn of z into natural log of z plus 1 by z minus 1 minus Wn minus 1 of z. This solution has logarithmic branch points at z is equal to plus minus 1, but any branch of the function is regular in the z-plane cut along the real axis from minus 1 to 1. We now define Qn of z in this cut plane by assigning to the logarithms their principal values. This solution is called the Legendre function of the second kind. Equivalently, we have Qn of z is equal to Pn of z multiplied by the integral over z going from infinity to z dz divided by z square minus 1 into Pn square of z. While evaluating this integral, the part should not cross the cut from minus 1 to 1. So students, let us summarize what we have learned in this module. We explained the importance of Legendre equation in physics and sketch its derivation from Laplace equation. We obtained the series solution of the Legendre equation for the case of integer values of parameter n appearing in the equation. We explain as to how one solution becomes a polynomial of order n, which is called the Legendre polynomial. We undertake a detailed study of the properties of the Legendre polynomials, derive Roderick's formula, study the properties of zeros of Legendre polynomials. We derive the generating function and obtain the recurrence relation. Next, we obtain integrals involving products of Legendre polynomials and thereby obtain the orthonormality property of these polynomials. Finally, we briefly discuss the complete solution of the Legendre equation. Thank you, students, for your kind attention.